So this is a completely random mesh. You can see that there is no preferred direction in the mesh, and if you were to use smear crack model, then could easily have a mesh bias. This is with a floating node method. You can see the cracks, they propagate along the 30-degree direction as planned. And then on the very same mesh, if we just change a different layup, this is the same mesh, and now it's a 0 degree. What we can see is that on the 0 degree ply, the mechanism changes completely. We have a longitudinal splitting. Then some of these panels would have a very quick, very sudden propagation of cracks, and you could see this kind of branching cracks. This typically happen in experiments in the 0 degree ply. And again, we change the layup on the same mesh to now a cross ply. On top, you have all the matrix cracks around the both 0 and 90 degree plies. On the bottom, you could see the delamination. See the high density of cracks. So this is because every edge is able to crack, so you could naturally capture many cracks. So you have a large network of matrix cracks and a large area of delamination. And last one is the quasi-isotropic. See that the cracks, they propagate independently of the underlying mesh along the respective fiber angles. Another example is delamination migration. So this is an experiment setup designed in NASA Langley. Here, the study is focusing on the propagation of delamination, which is originally on the lower interface between 0 ply and angle plies. And then as the crack propagates, the shear sign changes. Originally, when the crack tip is on the left of your loading rod, then your principal stress direction is promoting the crack to propagate along the original interface. But once the crack tip passes the loading rod, then the direction changes, and this stress state would try to promote the propagation of delamination onto the lower interface. When theta equals to 90, then we have a two-dimensional problem, and in 2D, both simulation and experiments confirmed that there is a nice regular single migration crack. But when theta changes to 60, for instance, then this is angle ply. What happens is that now your delamination migration is much less regular. You have many matrix cracks before the final migration, which shows that even though the stress state has satisfied the failure criteria for matrix crack to appear, but the energy state is not sufficient enough to promote the delamination from the lower to the higher interface. And one thing addition to note is that on the two sides of the specimen, the migration occurs on different locations. So they are caused by different matrix cracks, which further complicates the problem. So for this problem, I have designed a 3-ply 2-interface laminate element using the floating node method. I put them in the middle where delamination migration is going to happen, and then I simulated the problem. You can see the delamination firstly started on the lower interface, and then you can see all these attempts by the matrix cracks to kink up the delamination, but eventually it happens at a later stage than the first appearance of matrix crack, and then the migration is clearly caused by, in this case, 3 different matrix cracks.